Imagine if you could take all that carbon dioxide, the stuff we're always hearing about as a problem, and just flip the script.
Flip the script how?
Like not just capture it, but actually turn it into something useful. A building block for, say, the fuels of tomorrow.
Ah, okay. Yeah, that's exactly the kind of thing we're looking at today.
Right. So we're diving into this really new method. It claims to convert CO2 into carbon monoxide, which is key for synthetic fuels, right?
That's right. CO is a crucial intermediate. And this new approach promises to do it much, much faster and cheaper than before.
And this work comes from researchers at Hokkaido University, and also a company, AZUL Energy, Inc.
Yep, a collaborative effort.
So for everyone listening, you've got the details in your source materials. Our mission today is basically to unpack this. Why is it such a big deal for carbon neutrality? How does it actually work? And, what really makes it a potential game changer?
Sounds good.
Okay, so first off, turning CO2 into CO. That idea itself isn't brand new, is it?
No, not at all. People have been working on it for a while. But the older methods had some pretty significant drawbacks.
Right. Drawbacks like what? I think Lou Tenji from Tohoku University mentioned some specifics.
Exactly. Lou pointed out several key issues. First, the materials they needed were often expensive. Then there were problems with stability. The process wouldn't run reliably for long periods.
Okay.
Plus, selectivity was an issue. You weren't always getting just the carbon monoxide you wanted. And maybe the biggest hurdle, the preparation time.
Ah, yeah, the time. How long are we talking?
Often around 24 hours just to get the catalyst ready.
24 hours. Wow. Okay, I can see how that would make it really hard to scale up for, like, industrial use. It just sounds impractical.
It was definitely a major bottleneck. And that's really where this new research comes in, making a huge leap.
A leap in terms of speed?
Primarily, yes.
Yeah.
The core innovation is how they slashed that catalyst preparation time. From that 24 hours we just talked about, down to just 15 minutes.
Whoa, okay. 15 minutes. That's not just tweaking it. That's a whole different ballgame. That must open up possibilities.
It really does. It's a major benchmark for potentially scaling up.
So what's the secret sauce then? What are they doing differently to get that kind of speed?
Well, it comes down to two things, really. The specific catalyst they chose, and, maybe more importantly, a totally new way of applying it.
Okay, let's start with the catalyst. What did they use?
They looked into a family of compounds called phthalocyanines, PCs for short. They tested a few different types. Like ones without any metal in them, and then others with different metals, iron, cobalt, nickel, copper, sort of comparing them.
So they were experimenting to see which worked best for this CO2 to CO conversion. Did they find a clear winner?
They absolutely did.
Yeah.
Turns out, cobalt-phthalocyanine, that's CoPc, gave the best performance.
Cobalt-phthalocyanine, is that exotic or expensive?
That's the interesting part. No, it's actually a very common low-cost pigment.
Yeah.
So the best performer was also readily available and affordable.
Huh. That's fantastic news for potential costs down the line. Okay, so that's the catalyst. Now, you mentioned the application method was different too. I saw something about a graffiti-like spray technique. Sounds kind of fun.
Yeah, it does sound a bit informal, but it's actually quite innovative compared to the standard ways.
How so? What's the usual way?
Typically, you'd have to mix the catalyst powder with conductive carbon, maybe some binders, make a sort of anchor paste.
Right.
Then you apply that, let it dry, and then there's usually a long heat treatment step. That whole process is what could take up to 24 hours.
Okay, that sounds quite involved.
It is. But these researchers, they developed this simple spray technique. They just spray the catalyst solution directly onto what are called gas diffusion electrodes.
Gas diffusion electrodes. So those are the surfaces where the reaction happens, where the CO2 meets the catalyst.
Exactly. They're designed to let the gas flow through the catalyst efficiently, and by spraying directly onto them.
They skip all that mixing and drying and heating?
Pretty much. This direct spray method avoids those complex, time-consuming steps. And that's how they get the prep time down to just 15 minutes. It's a huge simplification.
Just 15 minutes versus 24 hours. The difference is stark. It seems almost too simple. Does this simpler method actually hold up in terms of, how well the conversion works? Performance?
That's the crucial question, right? And the data looks really good. They reported stable operation for 144 hours.
Wow, okay. That's over 6 days straight.
Yeah, and under a pretty demanding current density, too, 150 milliamps per square centimeter. That number tells you the reaction is happening at a pretty high rate.
Impressive stability and rate. How does it compare to other similar catalysts?
Well, They checked it against the DigCat database, which is basically the biggest collection of experimental data on these kinds of catalysts. And their CoPc catalyst, applied with this spray method, outperformed all the other phthalocyanine-based catalysts reported in that entire database.
Outperformed all of them. That's significant.
Very. And Lu Tenji, who we mentioned earlier, made a comment that really drives it home. He said their system exceeded the standard industrial thresholds for both reaction rate and stability. He called it the first ever to make the cut.
The first one, okay, that really highlights this isn't just a lab curiosity, it's hitting real-world performance metrics.
Precisely. It suggests genuine industrial potential. But they didn't just stop there at showing that it works well. They wanted to understand why.
Ah, right. The fundamental science behind it, always important. How did they dig into that?
They used some powerful tools. Synchrotron radiation, for one, at Japan's Nanoterasu facility.
Synchrotron radiation, that lets you see the structure at a really fine level, right? Almost atomic scale.
Exactly. It gives you incredibly detailed structural information. They combine those experimental observations with theoretical calculations.
And what did that reveal about this spray method?
It showed that the rapid spraying process leads to direct crystallization of the catalyst on the electrode. And this crystallization results in the CoPc molecules being packed together very densely.
Densely packed molecules. Okay. Why is that good? What does that do?
Well, think about electrons needing to move to the catalyst surface to make the reaction happen. This dense packing makes that electron transfer much more efficient.
I see. So the tight structure helps the electricity flow to where it needs to be for the CO2 conversion.
You got it. Better electron transfer equals better catalyst performance. So it really highlights that this direct crystallization achieved through the simple spray method isn't just faster. It's actually a key reason why the catalyst works so well. It's a strategy for making better catalysts.
That's fascinating. The application method itself improves the fundamental properties. Okay, let's zoom out a bit. What does this mean for the bigger picture? Climate change, carbon neutrality goals?
Yeah, the implications are potentially huge. Think about carbon capture and utilization, CCU. We capture CO2, but then what? We need efficient ways to turn it into something valuable.
And synthetic fuels are a major target for that.
Exactly. But making them economically viable has been tough. Partly because this CO2 to CO step was inefficient and expensive. This new method tackles that bottleneck head-on.
By improving energy efficiency and lowering costs.
Right. It could make producing sustainable fuels from captured CO2 much more feasible, maybe even bringing the cost closer to fossil fuels sooner than we thought. It could really accelerate the deployment of these technologies.
So it could be a really crucial piece of the puzzle for building a more circular carbon economy. It definitely sounds like a promising next-generation technology.
I think so, too. And for listeners wanting the nitty-gritty details, the paper is published in Advanced Science.
Great. So if we had to boil this whole deep dive down, what's the main takeaway?
I'd say the key takeaway is this. Researchers have found a significantly faster, simpler, and potentially cheaper way to kickstart the process of turning CO2 into a useful chemical building block, carbon monoxide.
Using that common cobalt catalyst and a surprisingly simple spray technique.
Yeah. And the resulting catalyst doesn't just work. It works exceptionally well, stable, fast, and potentially meeting industrial needs, largely thanks to how that spray method creates a highly effective catalyst structure.
And the potential knock-on effects for producing synthetic fuels, for actually using the CO2 we capture, seem pretty substantial on the path to carbon neutrality.
Absolutely. It really shifts the perspective on CO2, doesn't it? Maybe not just waste, but a future resource.
Definitely food for thought. Which leads to a final question for our listeners to mull over. If this simple spray-on direct crystallization works so well here, what other areas of catalysis, maybe in different industries entirely, could benefit from similar techniques?
Ooh, that's a good one. Or perhaps, thinking about the CO2 angle, if this scales up successfully, how fundamentally might it change how we view emissions, moving from a pure liability to, well, a potential feedstock?
Lots to ponder. Well, thanks for walking us through this really exciting development.
My pleasure. Fascinating stuff.
And thanks to everyone for joining us on this deep dive.